Hi, my name is Jennifer, and today I'm going to discuss our first physics lab, which examines an object in constant velocity. Constant velocity can be defined as an object moving at a constant speed in a constant direction. However, to further understand constant velocity, we need to look into Newton's second law, which states that a change in momentum is associated with a net force acting on the system. In my observation, the system is a billiard ball, while the surroundings are the table, my hand, the air, and anything else that may be interacting with the ball. From Newton's second law, we get the equation that net force is equal to the change in momentum divided by the change in time. In other words, the change in momentum is directly proportional to the net force on the system. Additionally, we can observe that momentum equals mass times velocity at low speeds. Now we are ready to examine the momentum principle in action on my billiard ball rolling across the table. The ball rolls in the positive x direction as shown. In an ideal system without any friction or push on the ball, momentum would be constant and the net force would be zero. We can see this in the diagram, that the only force on the ideal system is the gravitational force, which points directly downward and would not result in any change in momentum in the x direction. Thus, we will model the ball's motion without any net force. However, in practice, there is friction on the ball in the direction opposite of motion, both from the air and the texture of the table. The friction creates a net force, meaning that there is a change in momentum, and according to the equation momentum equals mass times velocity, the ball will slow down despite what we would expect from a ball with constant velocity. I modeled the predicted motion of the ball given that there was no net force on the ball, and thus no change in momentum and no resulting change in velocity. I used the GlowScript IDE in Python to create a visual model of the motion I expected to occur, as well as to generate the prediction of position over time. This prediction comes from iterating over the position update formula, using the ball's initial velocity that was derived from the first two position and time points from my observational data and tracker, with a small time difference as dt to find the instantaneous velocity shortly after I pushed the ball. If there were theoretically a net force, that could be plugged into the velocity update formula as well. However, we do not expect an object moving at constant velocity to have a net force. This program could continue endlessly, with the ball continuing motion in the x direction forever since there is no net force and the velocity is constant. However, I only plotted points for 1.35 seconds, since that is the length of my observational video. The slope of the position time graph is the velocity, since the units of velocity are meters per second, or rather meters divided by seconds. In reality, the ball appears to have a constant velocity to our eyes, but the frictional force does slow the ball down, even within the time frame that I have examined. To demonstrate this, I used Tracker to analyze my video and graph the position of the ball over time. The distance in the video was initialized by the diameter of the ball, which was 57 millimeters. The portion of my video that I examined was from the 11th frame to the 51st frame, taking the middle section in order to minimize error that may have come from my initial push on the ball or the eventual stopping of the ball due to the frictional force. I converted the data from the table and tracker to SI units in Excel to prepare for data analysis. When the graphs of predicted and observed motion are imposed onto one another, it becomes apparent that there is a large discrepancy between the expected and observed velocities. Notably, the difference between the two lines grows over time. To explain this, we need to return to the momentum principle and the consequences of a net force, friction, on the ball's velocity. The table I rolled the ball on had a rough felt texture, which contributed to the ball experiencing the frictional force that increasingly slowed it over time. Revisiting the equation that net force is equal to the change in momentum divided by the change in time, we can see that the ball loses momentum over each time interval. The amount of frictional force is constant throughout the time interval, so the change in momentum is constant as well. Since the mass of the ball is constant and momentum equals mass times velocity, we know that the change in momentum is going to be directly proportional to the change in velocity. Thus, we see a steady decrease in velocity over time, as the observed position over time increasingly strays from our prediction of the ball's motion in truly constant velocity. One of the best ways I could have limited the discrepancy between the observed and predicted positions over time would have been to roll the ball on a smoother surface, such as a wooden table or a tile floor. These smoother surfaces would have limited the frictional force, and the observed positions would have matched the predicted positions more closely and for a longer period of time, since the net force would have been lessened. So overall, we've learned from this model that real-life physical systems have complex interactions with their surroundings that are typically more complicated than an object moving without any net force. Even though the ball appeared to be moving at a constant velocity to my eye, there were invisible forces at play that I could really only understand by comparing my findings to a computational model. Despite the fact that my data did not fit the model, understanding what conditions yield constant velocity through Newton's second law helped give us the foundation that we need to understand forces in more complex and oftentimes more realistic situations.